Hello everyone, this is SM Abid Hassan and today we will discuss about the airfoil experiment from course ME 4621. So let's start our presentation. At first we will discuss about the objectives of this experiment. So here we need to determine experimentally the lift force per unit width of provided airfoil as well as the lift coefficient. Later, we need to experimentally determine the pressure-induced drag force per unit width of the airfoil and the relevant drag coefficient. After that, we need to estimate the angle of attack for flow separation of the airfoil, and then we need to prepare a lift drag polar for the airfoil. Finally, we need to compare the results with theory and comment on their validity. All of these tasks should be carried out for different angles of attack, which is alpha. Let's discuss about the measurements and cases. In this experiment, we need to measure these things. At first, the inclined manometer oil level, which is calibrated in water level. We need to measure the vertical manometer oil level corresponding to different point pressure taps on airfoil. Finally, we need to measure the angle of attack of the airfoil. In terms of cases, we need to measure this experiment at 8 different angle of attacks with the range of -8 degree to 20 degree. Later, we need to record the pressure values at predefined points along the top and bottom surface of the airfoil. Next, we will discuss about the experimental setup. So here you can see a subsonic closed loop wind tunnel. On top of it, you can see a motor-driven fan, which can also be controlled by using a LabVIEW software, which is located in this computer. And we will use this computer to acquire various data. Next, we have an inclined manometer. And then here we have a vertical manometer. And here we have the airfoil stand and the test section. We will discuss about these components separately. At first, we will discuss about the airfoil stand and test section. Here we can see the pitot tube. The pitot tube position can be controlled using a motorized system followed by a control from a LabVIEW interface. However, considering the airflow pattern and to avoid any flow discrepancies, it is recommended to position the pitot tube 12 inches above the bottom surface. Next, we can see a 3D printed airfoil, and here we have an adjusting knob for angle of attack. By adjusting this knob, we can change the position of the airfoil. And these are connected with the vertical manometer, which gives us the pressure tap points of the airfoil. Next, we have the vertical manometer. The pressure along the airfoil surfaces are measured using this vertical manometer. The first section here corresponds to the airfoil surface, whereas the other section here corresponds to the bottom surface of the airfoil. The first two tubes here and the last two tubes here basically provide the required reference oil level corresponding to the ambient pressure. During your calculations, only one of these four reference oil levels which will be in your data can be used to estimating the pressure. Later we have the inclined manometer. The pitot tube which we showed earlier is connected to an inclined manometer. The kinetic head is converted to pressure head and it is measured as the oil level in the inclined manometer. However, the manometer fluid is red oil, whereas the scale is calibrated in inches of water. So you would be using the water properties for calculating the airspeed. Then we will discuss about the theoretical concept of this experiment. The essential part of the experiment is to measure the lift and drag force. There are 16 pressure taps, 8 on top surface and 8 on the bottom surface of the airfoil. For a sample pressure point such as point 2, the coordinate of the adjacent pressure tap location point 1 and point 3 are utilized to evaluate the area and angle of inclination. The procedure differs slightly for leading edge and trailing edge points as shown here. For the pressure point 2, the pressure is assumed to be constant over the entire area, which is required to evaluate the normal and axial force components. The total normal and axial force is evaluated by summing the force contribution at all pressure tap locations. However, this total and axial force is utilized to calculate the drag and lift force on the airfoil, wherein we use the angle of attack value of the airfoil. This is the user interface of the software. Here we can see a lab view interface in order to control the fan. So when we need to turn on the fan, we need to use this. Here, this is the traverse position control, which basically controls the pitot position. So like we said earlier, it is recommended to position the pitot tube 12 inch above the bottom surface. So we can control it from here. And from this, we can see the pitch angle, which will be changed whenever we will adjust the knob. So next we have the pitot tube position control. Like we said earlier, we need before starting the experiment, we need to position the pitot tube 12-inch above from the bottom. Next, we will show how we can change the airfoil angle of attack. So you can see by adjusting this knob, we can change the position of the airfoil. However, from the user interface, we can find the exact angle of attack. Next, we have the incline manometer, and here we will see a video how the value in incline manometer changes. So we started the fan, and once the fan is started, the air speed increases with the time, which will reflect in the depression in the oil level of the incline manometer. So you can see there is some change in the incline manometer reading. You can hear the fan noise increasing. So we will wait till the stable final level has been reached. As it seems, this seems to be a stable level. So the stable final level of oil read as inches of water will be used to calculate the final air speed. Next, we have some information how the air velocity calculation will be done. So here we have a barometric pressure reading, which will help us to use this air velocity calculator. So you can see all these instructions here. So after getting the barometric pressure reading, we also need to find the relative humidity, which can be found in the lab. So we need to set this black point to the relative humidity of our condition, and then we will get the correction factor. After that, by using this barometric pressure reading and the room temperature, we will get the air density. And here we will get the air velocity by using the reading from the inclined manometer. Next, we will see the pressure distributions from the test model pressure taps. So here we will start the fan and you will see there will be some changes in the vertical manometer. So you can hear the noise of the fan which is increasing, and soon you will see some changes in the vertical manometer. We need to perform this experiment from -8 degree to 20 degree with 4 degree of variation. So by adjusting this knob, we will change the position of the airfoil. As mentioned earlier, the right hand side basically focuses the bottom surface of the airfoil, and as we are increasing the angle of attack, you can see there has been some change on the left side which is correspond to the top surface of the airfoil. However, as the angle of attack is increased beyond 15 degrees or so, at a particular angle of attack you will notice the top airfoil surface pressure significantly increases. The initial angle at which this trend of pressure increases strut is identified as the stall angle. So here you can see the top airfoil surface pressure significantly increases. However, your data will have an observed stall angle, which can also be verified by plotting the lift coefficients against the angle of attack, where you would observe a decreasing trend at and after stall. You will be given the pressure data for this experiment. Use the pressure data to evaluate the lift and drag force along the airfoil, plot the respective lift and drag coefficients, and determine the stall angle for this particular airfoil. Once you are done with the experiment, turn off the fan. Thank you.